Good morning and welcome back to students that are joining us from 225, or if you're a visiting student at Lake State, welcome to you. Every single day we'll start the morning with announcements, and for tomorrow what you should be watching is chapter 13 parts A and B. So we'll start with alcohols and phenols tomorrow, and for today hopefully you've already watched chapter 12. Every single week we'll have homework available, and that will cover the week's problems. And your first homework assignment is available, but won't be due until June 29th, which is next Monday. You could get a start on it, or you can just wait until later in the week to do so. And you can find the video on Moodle for submitting assignments if you're not sure how to do that. Lab 1 is available, as is Lab 2. That content for a lecture we haven't started yet, so you might want to hold off until at least tomorrow to do your labs or to start them. And there's also a tutorial video for Beyond Labs on how to use that if you haven't already. So the Lab 1 is due on June 26th. Lab 2 is due on June 28th. And every single week we have either a quiz or an exam that is due. This week we have quiz 1, which will cover chapters 12 through 14. That will open at midnight on Thursday, and it closes on Friday at 11:59 p.m. You can see our meeting ID and password, and you should be able to access this as well in the Moodle page. Our office hours are before and after class, so I'm usually here, or at least on the computer, half an hour before and then a little bit after class. And you can also email me by appointment. Sometimes if it's something that I can answer quickly by email, I can do that. Otherwise, we can schedule a Zoom appointment and do it that way. The required text for this class is the course pack, which is available in the bookstore. So this is the course pack that you'll find in the bookstore. Hopefully you already have it. Something else that is required for classes, not required I guess, but is very helpful is your reaction book, which the ones that are continuing on are familiar with already. This is available on Moodle, and all of the reactions that we did in Chem 225 are in there right now. So I posted the scanned copies of that so you can see what reactions you should be caught up on for this semester. Or if you wanted to recopy your reaction books and start over fresh, you can do that as well. And so those are there. And you also need to purchase the Beyond Labs Virtual Chem Lab subscription. If you purchased it for last term, that subscription is good for a year. So you should be able to use it for this class as well. If for some reason, I don't know what other classes you would take after this that would require it, but if you took the class at a later time, that subscription is good for a year for any other class as well. The recommended text is Organic Chemistry by David Klein, which I don't have a copy of here. That's where the problems come from, and a lot of the notes are the content and the order of the things, but I don't require the book just because we have the problem sets already in the course pack. All right, so Moodle is going to have everything that you need on the class page, and I'll show you that right now, actually. This is the Moodle course page. And you can see there's the link to our Zoom class. The syllabus is posted there as well. And on here, you'll find links for our lecture videos. Those you've already hopefully have accessed. A live session recording, so after this class is over, the live session will be available here. The CPAs, which we have, we'll go over at the beginning of every class. There's nothing that you have to turn in for these. These are just questions that come up, and we'll discuss those at the beginning of class. Your homework that's available is here. You can see the links for how to submit an assignment. And then you have your week 1 homework is right there. So that one's where you can click to find the homework assignment. And then there's the reaction books as well. And then your problem set solutions will be here on this page as we go through different ones. For every single chapter, I also do extra problem video solutions. So there's extra problems listed in the lecture videos. And then here you'll find the links to the extra videos. You can have somebody walking you through the problems if you need that. And then there's quizzes and exams. And then here are your lab resources. So there's a lab report and notebook example for this course, and also the lab notebook. And then here's a link on a video to watch or to watch to figure out how to use Beyond Labs if you haven't used that before. And for those of you continuing from last term, there's a couple of changes in the lab notebook that you may want to check out. You can just open the lab report for that. Okay, so this is just a continuation of Organic 1. So we're going to look at lots and lots and lots of reactions. And you can look at the learning outcomes there, but it will include a lot of synthesis. This is our tentative course outline. So we have a 6-week condensed class. We're going to be covering 2 to 3 chapters per week. And you notice that's a little bit different pace from last term where we maybe did a couple more chapters than that. But we'll be spending about 2 days on each chapter and practicing problems within that. Like I mentioned earlier, every week there will be a quiz or an exam due. There's 2 exams, and then your final exam is cumulative, and that's due on the last day of summer class. And you can see the grading scale below. Your quizzes are worth 30 points each, and you get points for homework and participation. And then there's the 2 exams. We have lab. And for our lab, it's 200 points, and there's a synthesis project at the end, which is usually what I do with my students in lab, where you come up with a big synthesis for a large molecule, which you will be assigned. Any questions yet? All right, and then there's the course policies. Your best way to get through this class is coming to the live lectures so you can ask questions. Completing your assignments on time is also very important, especially with the way this class is. Getting behind is not great, especially how fast we move. And with late penalties, you don't want to incur those if you don't need to. So those points will add up if you're constantly late with your assignments. There's no makeup quizzes or exams unless you have pre-approved reasons. And the final exam for this course is scheduled on July 30th, but I believe I'm giving you till the 31st to do your final exam. So you have those 2 days to do that. So to succeed in this class, you want to manage your time well, make a schedule. If you have a job or no job, you kind of want to treat this as a way, it's not an afterthought. You really have to dedicate yourself to organic chemistry. So make sure you know when dates of quizzes and exams are occurring. You want to watch the assigned lecture video before coming to the live session. That way you'll get the best out of the live session. Attempt the CPAs or if you have time, do the suggested problems before then. And then come to class and participate. So if you're asking for questions, try to throw out an answer and ask lots of questions if you can. You're probably not the only person that has a question that's of the same type. So it's probably helpful for everybody if you do ask that. I definitely would not wait until the night before the exam to study, and also do not get behind in class. You are allowed to use your notes and the reaction book for the exam, but it's important to know how to use those notes and where to find things as well. So don't just rely on the fact that you have that as a crutch. So you want to study the material, do lots of problems, because doing problems in organic chemistry is the way to get through this class. It's kind of like studying for math. You're not just going to know how to do it by looking at it. And unfortunately, there's not a synthesis calculator where you can punch in structures and get something out on the other end. All right, so lectures will be posted online. I don't keep track of who comes officially. I do notice when people are missing or are here or not there. For those of you that are attending via, if you're watching the videos after, I definitely can't keep track of that. Not very well, but it's on you to come to class and stay caught up. This semester, I'm not doing the words of the day, so hopefully people aren't disappointed by that, but I won't be keeping track of those either. Your class participation points I mentioned, those aren't points that are assigned, but it's just problems that will help you kind of focus on what's going to be in the videos. And those are also problems that we'll go over at the beginning of each class. So you have your homework that I mentioned. You're welcome to collaborate or talk to other students about homework assignments. There is on the Moodle page a message board. If you want to start asking questions there with students, you are perfectly welcome to do that. there's a couple of different message boards there. 3 quizzes are scheduled. Those you can find on Moodle. Like I mentioned, you can use notes or your reaction books on the quizzes. You cannot use the internet. You can't use SciFinder. Other students in the class are not allowed to help you with the quiz or using other resources. So you can use notes from the class or the reaction books. And you'll have until almost midnight on Friday to submit these to Moodle for each of those assignments. Quizzes are timed. You have 90 minutes, which should be lots of time. In a typical class, I would allow 15 to 20 minutes on the quiz. So the 90 minutes is allowing you for, technical difficulty times. So once you open the assignment, though, you have to be ready to do it because the time does start ticking. And you have that 90 minutes to do the quiz, print it out if you need, and then submit it. And then exams, a similar format, but you have 3 hours to do your exam. Questions so far? All right, your final exam will start on Thursday, July 31st, but you'll have till Friday to do that. I can fix that and then post that syllabus. And then here's your lab syllabus. And that's going to be with Virtual Chem Lab on Beyond Labs. So I mentioned that subscription. Again, the subscription was $25. Hopefully it's still $25 for that full year. And if you notice, we're actually done with the experiments on July 16th. And then we'll start working on the retrosynthesis and the total synthesis project. And that's that 100 points there. Okay, anybody have questions about the syllabus up to this point, or if I've missed something, this is your opportunity to ask about that. All right, no questions. So I'm going to jump into our chapter 12 recap. So the nice thing about starting this semester with chapter 12 is that it's a synthesis chapter, which is really a review of reactions from last semester. So I'm not going to go through all of the reactions, but we'll look at quite a few of them. And so since we're looking at the synthesis, we can start with solving one-step synthesis. And so for this particular reaction, you want to think about what reactions do we have in our arsenal of reactions that will get us there. So you want to look at what is different about this reaction. So here we're going from an alkene to 2 functional groups. We have a Br plus a hydroxy here. And then our carbon count is the same, so we don't have to worry about adding carbons. So then you want to look at what reactions do you know that will get you to this product. All right, so I see a question now. Sorry to backtrack here. The retrosynthesis and total synthesis, are they separate or cumulative? The whole synthesis project is worth 100 points. The retrosynthesis is kind of like a rough draft for the total synthesis, and so that will be a portion of the 100 points. All right, so getting back to this synthesis here, we notice that there's a hydroxy and a Br, and so you want to look at what reactions you have in your reaction book that will add both of those things, and this is a one-step synthesis. So if you remember, this is going to be Br2 with water. And so that's how you would do a one-step synthesis. We're also going to look at retrosynthesis of larger molecules, where we have to work backwards for a multi-step synthesis. So you'll want to look at your beginning compound X to see how many steps there are to compound A. And then we have our look at how many functional groups are changing. Are they changing in the position? Are carbons being added? So those are kind of the 3 questions that you want to ask when you're looking at a retrosynthesis. So if we were looking at this particular retrosynthesis, you don't want to get bogged down with, I don't know what I'm doing, there's too many things going on here. What you want to do is look to the step just before. And so we have the alkyne is one way that we know how to make a ketone at this point. After tomorrow's lecture, we'll figure out other ways to make ketones. But this is what you want to do, is to go to think about what reactions do you know how to make a ketone, one way that you know how to do it is to make an alkyne. Then go back one step before that. What is the way I know how to make an alkyne? Well, I can make an alkyne using 2 Br groups on there. And I can get to 2 Brs from the alkene. So then think about what reagents you can use. So Br2 will add 2 bromines to an alkene. And then to do an elimination, we need excess sodium amide, and then followed up with water. And then to get to the ketone, we use mercury sulfate, water, and then sulfuric acid. So that's kind of how we get through our retrosynthesis, is to work at what comes just before that last thing there. All right, does anybody have questions so far? All right, there's no questions here. And at any point, if things are moving too quickly, you can always ask me to slow down. We can do that as well. Because if there's no questions, I assume everybody knows what's going on, and then I'll just keep pushing through here. Okay, so on the CPA, there was this particular reaction wheel, we'll call it. And so you can look at an alkene and figure out what can happen with each of these reagents here. So I'm going to start at this particular one here. So if I have an alkene, I'm going to add chlorine plus water. And this is similar to the reaction that we did a couple of slides ago. And in place of bromine, we're using chlorine. So this is going to add a Cl, and it's also going to add an OH, except that our OH is going to be on the more substituted carbon. So that would give me the Markovnikov product. So the OH will go here, and that usually adds opposite direction to the halogen. So we'll have that one there. And I just turned my cycloalkene or cycloalkane chain to the side because I can't draw sideways cyclohexane rings very well. So the answer is the same. I've just changed the way that I've drawn it there. All right, so for mercury acetate, this is going to add a water, and that sodium borohydride is going to remove the mercury. So again, I'm just going to draw this out here. And the OH is going to go to the Markovnikov position as well. And the BH3 is going to be our reagent that reverses the regiochemistry. So if you want your alcohol on the less substituted position, that is when to use BH3. So my carbon number hasn't changed, and our reaction is only occurring where the alkene is. So I shouldn't be adding OHs to this position here just because it's on the end. It's just the less substituted carbon of the alkene. All right, does anybody remember what H2 and nickel does to an alkene? All right, so H2 and nickel will reduce the alkene to the alkane. So we just have single bonds there. And then for Br2, that's going to add 2 bromines and they're going to add anti to each other. So you can have the Br here and this Br here. We'd also get the enantiomer of that. All right, any questions here? All right, here we're going to look at some more reactions here. These are reactions of alkynes, so they're triple bond. And I'll just start at the top here. 9-BBN is similar to borane, so this is going to give me an anti-Markovnikov product. And that's going to have first form the enol. So it adds an OH to the double bond, which will tautomerize to the aldehyde. So that's the anti-Markovnikov product. And just for fun, we'll go counterclockwise. If we add excess Br2 to the alkyne, that's going to add a whole boatload of bromines. We'll actually get 4 added where the triple bond was. And then we have our alkyne with H2SO4 and water with mercury sulfate. That is our Markovnikov reagent. We'll first form the enol, and that will tautomerize to the ketone. Sodium amide with an alkyne, that's going to first form a negative charge here at the end of the alkyne, which can then attack this group. So we add the CH2 plus the pH, which is the same thing as a benzene ring. So that's pH. And notice our triple bond is still intact. So when you add a new carbon, nothing else happens to the triple bond other than we add the new carbon. So it doesn't get reduced or anything like that unless we add more reagents. HBr plus peroxide, this is our anti-Markovnikov reagent. So we're going to add Br to one side, the less substituted side, and the H goes here. Ozonolysis followed by water is going to cleave that in half. We're going to end up with CO2 plus a carboxylic acid. So 1, 2, 3, 1, 2, 3. And then with HX1 equivalent, that's the Markovnikov, so we'll get the alkene, and our halogen goes there, and a hydrogen goes here. All right, any questions on those reactions there of alkynes? All right, if any, for some reason, those reagents or reactions are new to any of you that are joining us that weren't in 225, you can just let me know and I can direct you to the lecture videos from last term. All right, so we're going to look at some synthesis problems now. So this is one of the synthesis problems that was put on the board before. And so take a second or a couple of minutes to look at the synthesis that is proposed here. And you can determine if the synthesis looks good or if there's different steps there that are problematic. So I'll put up a poll here and you can tell me what you think. All right, so there's a couple of different things going on here. I think everybody agrees that the first one is not an option. So this synthesis is not going to work as it is written. And so we can look at the next one to see, let's fix step Q. I think there was a drawing mistake here. This should have been that one. All right, so the Q is the problematic step on the last synthesis. If I had drawn the other problem incorrectly there, I apologize. So how would we fix step Q? What is wrong with HBr in that step? How would we fix step Q? All right, so most of you want to use either the addition of heat or light, use Br2, or use Br2 with heat and light. So the reagent HBr we've seen used before, and you could use HBr. Oops. If you had an alkene present. But the alkene is not present here, and we need to use something else. And our something else here is that we have to use a radical reaction to insert that bromine there. So we're going to use Br2 with heat or light. So we can't just use Br2. That's another reagent that will add 2 bromines across a Br. So we don't need the Br2, or sorry, we need the Br2 with heat or light. There was a question about, does it need peroxide? Peroxide you could use to start, a radical reaction, but it's usually the HBr is what you would use to do the anti-Markovnikov addition. So for, if you had something like this, then we can use that to add the Br on the less substituted position. So that's generally what we use the peroxide for. To add a Br2 or a bromine to a alkane that doesn't have any functional groups, we want to use heat or light. That will be better at initiating that reaction. So for the next step in the synthesis, then we take acetylene, which is C2H2. We add sodium amide, which will create the negative charge here. And then we add in that bromocyclohexane which we just made, kick that off, and that will form this product here. And then we can use H2 Lindlar in order to get to that alkene. You could also, if you were trying to do this reaction, use Na with liquid ammonia. And that's a terminal alkyne, so the stereochemistry doesn't matter there. All right, other questions on this synthesis? All right, here is another one. We're going from methyl cyclohexane to something with 2 carbonyls. So does this reaction look like it's going to work, or is there something that is problematic here? All right, so most of you thought that step C will not work, or letter C, aka step R, and that would be correct. So that one is not going to work. Br2 with light, which we just saw, is going to add the bromine to the most substituted position, which is that one right there. Something is fishy about the t-butoxide step, and then the last step will be ozonolysis, which cleaves that bond in half and opens up the ring. So let's look at what ways we can fix that. So how would we fix this reaction, step R? All right, so we have a tie between B and D. So we don't want to do ozonolysis first. That's actually not going to do anything for our reaction. And that is because ozonolysis works on double bonds and triple bonds. And we don't have either of those there. And so that one's not going to work. B, we do want to use a smaller base because if we use t-butoxide, we're going to get this product right here. So this is going to be the result of t-butoxide. So we want to use DBU, which will give us the most substituted alkene, which is the one that is shown there. So the ozonolysis step is fine. Some of you chose, so C is not going to work either. If we did ozonolysis on this product here, we would get a ketone plus formaldehyde. And then if you want to use NaOET as a base, that one sometimes acts as a base, but a lot of times that can result in a mixture of SN2 plus E2 products. So if we want a surefire way to get to our elimination, you want to use something that's going to act as a base only. Sodium ethoxide can act as a base or a nucleophile. Any questions on that problem? All right, here we're looking to propose a synthesis for each of these transformations. Okay, so observations that we might make on this particular one. Our carbon number is the same. We've just shifted our bromine. So our bromine was on the end and now it is over to the middle. So if you would like to, there was a question, sorry, DBU stands for I don't remember, diazobenzene something or other. But DBU is a strong base that is a small base. So that is the question there. So DBU is something that acts as a base only. The structure, again, I don't remember off the top of my head, but it's a small base that acts as a base only. All right, so we've shifted our bromine. So you can move in the forward direction if you know where you're going. If you're not sure, you can do the retrosynthesis. And think about what reagents that you know how to put this here. And if you go, we know that we can make a Br from an alkene. So I can make it from that alkene. which I can do from something with a leaving group at the end, which happens to be our starting material. So if we're going in the forward direction, in order to get to this intermediate A, I need to use a base. And in this case, you can use any base because it is on the end, but I'll just use sodium hydride as my base. That will eliminate this proton. Which will form that double bond and kick off the bromine. And then to get to this product here where Br is on the more substituted carbon, I just want to use HBr. So that is a two-step synthesis. We do an elimination and then the bromination. Okay, any questions on that particular synthesis? All right, this next one here, we're looking for transformations, and we're just switching OHs. So our OH is switching. All right, so if we're doing a retrosynthesis here, I can make an OH from this alkene, which in a couple steps I could get from here. So there's a couple of ways to do this particular synthesis. The one way that you can do it is doing an elimination of OH. And if you remember, OH is a bad leaving group. So what we can do is convert it to a better one. So we use TSCl, or tazol chloride. And so you use have an OTS there, which is a good leaving group. Then we can do our elimination. And here the size of the base does matter. If I use T-butoxide, that will grab HA, which I don't want to do. I want it to eliminate HB. So I use my small base. Again, you can use sodium hydride. DBU works here, or DBN. So this base is going to grab this hydrogen and kick that off. So we do our E2 elimination. And then to get to here, we can just add H2O with H2SO4. And that is one way that we can do it, just because our OH is on the more substituted carbon. That would form a tertiary carbocation, so I don't have to worry about rearrangements. If you did have to worry about a rearrangement, you could use instead the mercuric acetate with water, followed by sodium borohydride. All right, questions on that one? Another way that you could do this elimination step without doing the OH is to do an elimination under acidic conditions. So if you use H2SO4, water and heat, actually don't want water, H2SO4 and heat, what that's going to do is protonate that alcohol, which will promote it, turn it into water, which makes a good leaving group, and then it will do an E1 elimination. So this would be an E1 if we did this way. So you could bypass that, converting it to a better leaving group. Now this will only work because we're forming the most substituted alkene here. If you're trying to put the alkene on the end, then that would not work as well. So that one you want to be careful of. All right, other questions here? All right, why don't you give a shot at this particular synthesis. So this is very similar to the one that we just did. Our OH is shifting, but the direction that is shifting is a little bit different. So what do we need to do differently here? All right, would this synthesis work as I've written it? Okay, so if you are chiming in with no, what do we need to fix in this particular synthesis? Okay, so we need to use a different reagent in the last step. That last step is going to, that would actually make a lot of different products because we could have rearrangements there. And so the reagent that we want to use is one that is going to give us the anti-Markovnikov product. So we want to use BH3, THF, followed by peroxide and hydroxide. Very good. Any questions on this particular problem? So tosyl chloride makes the OH, which is bad, into a better leaving group. T-butoxide is going to give us the less substituted alkene. You could also actually have used DBU here because there's no beta protons here. But to be safe, if you want to use T-butoxide, you can do that. And then to add the alcohol to the anti-Markovnikov or the less substituted product, we use BH3. Okay, in this problem, we make our observations. We're adding 2 carbons there. And our bromine is gone. All right, so this one is going to require a little bit of backwards thinking. So I have Br here. and I need to add an alkyne. I do know that I can add things to an alkyne. If I add NaNH2, and then some R group with Br, that will leave me my alkyne plus a new bond to the R group. So in this case, the group that is being added, that is the R, is this whole thing right here. So I actually don't have to do anything with that RBr. I just need to find acetylene. So I have my acetylene, use sodium NH2. And then use that beginning starting material. So my negative charge will form there. I'll take this and kick that one off. And if you wanted to draw it to look like the product, you can. That's what you get there. So don't get fixated on having to convert the beginning starting material into the end thing. Sometimes you have to bring something in extra, and that's going to be this reagent A here will be something that is over the arrow and not necessarily what you're starting it with. Does that make sense? Any questions there? All right, let's look at the next problem here. So identify what reagents that we can use to solve this problem. Our observations. I'm going to count my carbons here. 1, 2. All right, so I'm adding 3 carbons. I have a double bond. I'm going to renumber these over here. So the functional group location in the starting alkyne is between 4 and 5, and it's between 4 and 5 in the alkene as well. So we don't have to worry about shifting functional groups. We're just going to have to reduce that. So what we need to do is add carbons. And if you recall from the last term, when we're doing synthesis, we want to work on adding our carbons first. And the carbons that we're adding are these ones right here. So I need NaNH2. And I'm adding 3 carbons. So I have 1, 2, 3, and then add my Br. You don't have to use bromine. You can use chlorine or iodine. So the product of that reaction is the addition of my 3 carbons. And what reagent do I need to form that alkene with the Z stereochemistry? What reagent do I need there? Very good. We want to use H2 Lindlar. That's going to give you the Z stereochemistry, or the cis. Good. Any questions on that one? All right, how about this one? Give you a couple minutes to work on this one here. You're going to have, we're adding carbons. 2 carbons. And the functional group is in a different spot. So you can have a couple minutes or minute or two to either strategize or actually come up with the synthesis, or if you want to talk out loud in the chat with your ideas there, maybe you guys can collectively come up with the synthesis. All right, any ideas? Is anybody's synthesis starting to have a lot of steps? All right, so some students, when I give them this problem, will start to add the carbon. So maybe you started with adding the 2 carbons. Like that. So you have your addition of 2 carbons, and then you start working towards shifting that alkene, or I'm sorry, the alkyne to the end. And so then you reduce this to the double bond, maybe use H2 Lindlar. Add your Br to this one, and then you do eliminations to try to get that way. So maybe some of you are on that track. There is a shorter way, which is where you start to think about these reactions or these syntheses a little bit more abstractly. What I can recognize is that I added only carbon 6 and 7. So what if 6 and 7 were the alkyne, and the other thing I was adding was this. So now I just need to go from my starting material of the alkyne to this Br on the end, and then I can add that 2 carbon acetylene. So let's do that. I need to make my alkyne. First, I need to do my double bond. So I can use NaNH3, which will make the double bond. The stereochemistry here is irrelevant because it's on the end. And then to put my bromine on the end, I want to use HBr plus peroxide. And then now that I've made this, we'll call that A, then I can start a different synthesis with acetylene. Use NaNH2, and then insert A, or this guy here. to get our target molecule. So you want to get yourself away from trapping yourself into the starting material being always the thing that you're adding onto. Sometimes that's getting added to it. All right, any questions there? All right, how about this one? Reactions that we know how to make in aldehyde. How do we make an aldehyde? What was here before that? Good, so we had an enol before here. And then how do we get that enol? That's one way to do it, right? Other things that you might notice, did anybody count the carbons? So we're losing a carbon here. So if we were doing the enol, in order to do that enol, we would need to have an alkyne present, which in this structure, I have too many bonds to carbon. So this way is not going to work. Also, we're losing a carbon. So we want to rethink our synthesis here. Anybody have other ideas? What's another way that we can use to make an aldehyde? Right. Does anybody remember ozonolysis? So if we had ozonolysis, we would just need this, and then we would cleave that in half in order to make that ozone, which we could make from the alcohol. That is present there. So if we're going to do that synthesis, we need to make our OH a good leaving group. So I'll tosylate that. And tomorrow we'll learn new ways to make a better leaving group that's not tosyl. So now I need to make or do an elimination. And if I want to get the alkene on the end, I need to use T-butoxide. And then after that, I can do the ozonolysis. So I'll get the aldehyde plus formaldehyde. All right, any questions there? Right, that was all of the in-class problems that I had assigned at the end of the video. If we want, we can look at a couple more synthesis problems, or if your brains feel like you're full after the final exam, or if you're just joining us from, you haven't had class in a while, we can just stop there for the day. So if you feel strongly about continuing and doing a couple extra problems, I can find some real quick. Otherwise, that's what we have for the day. There'll be another video with extra synthesis problems if you just want to take a break for the day and come back to those later. All right, does anybody feel strongly either way? All right, so there's a vote for another problem. So I'll find one quickly here. So if you have to go, that's completely fine. If you want to stick around for a couple more problems, that is fine as well. Just give me a minute here. I'm going to pull from chapter 12, number 15, a couple of those problems. All right, so this is chapter 15 or chapter 12, number 15A. So here's one where we're going to propose a synthesis for each of these transformations. Make that a little bit bigger there. All right, so our observations for this one. We have, let's see, this is very similar to the last one. 1, 2, 3, 4. All right, so I've lost a carbon. And I'm also ending up with the carboxylic acid. All right, so if I think about what reactions I have where I can lose a carbon and form a carboxylic acid, the first one that comes to mind is one where I'm doing ozonolysis on an alkyne. So if I do ozonolysis on an alkyne with the water workup, that gives me the carboxylic acid. So what I need to do to get to that alkyne is I need to do a double elimination. And in order to have a double elimination, I need 2 leaving groups. So I can add Br2 and that will add 2 bromines. And technically this would add them anti to each other, but because we're eliminating them in the next step, I'm not really concerned about the reach or the stereochemistry there. So then in order to form the alkyne, I use excess NaNH2 followed by water. And that will form the alkyne. And then to get to this step, we use ozonolysis followed by water. Questions there? All right, let's look at another one. All right, same directions, different synthesis problem. If I look here, 1, 2, 3, I'm adding 2 carbons. I have an alkene. And my starting material has no functional groups. So I need to put one of these in. One of the things that you want to look at also is the location of the functional group is between 4 and 5. And if you can look at the starting material, this part right here, this isobutane, is this one right here. So I'm adding carbons 4 and 5. So I'm going to think of this as acetylene plus that right there. I think that will make things a little bit easier to try to add. And then I don't have to worry about moving my functional group all the way to 4 and 5 from wherever I would have added it to the beginning materials. Okay, does anybody have any questions on how I got to that? Okay, so to do our forward synthesis, we said that there are no functional groups, so I need to put one in place. And ideally, I want to put it on the carbon that's labeled 3, but we don't have any reactions right now that will put it on that end unless you added chlorine, which could do that, but then you'd have a whole bunch of mess that you'd have to isolate. So what I can do is add Br2 and light, or heat, and that will add the bromine to the most substituted carbon. We can then do an elimination with base. So I'm going to do an E2 and use sodium hydride. So that will do my elimination. And I want to add Br to the end. So I use HBr plus peroxide. That will add Br to the end. So at this point, I've isolated that product, and then I'm going to start a new reaction with acetylene down here, NaNH2, and then add that alkyl halide that I just made. All right, and then I need to get from that alkyne to this alkene. Then you can use whatever reducing reagent you want. So if you want to use the NaNH3, you can use that one. And then H2 Lindlar would also work in that case. All right, should we do one more? All right, so let's do one more here. Let's do number 18 in the book. So acetylene is our only source of carbon atoms. So this is going to make things a little bit trickier because we can only use acetylene to add carbons. So we can't just add any carbon chain willy-nilly. So this one will take us a little bit of time to get there. But if we're going to make our initial observations here, I have 2 carbons. I need to add 8. And then I need to put a functional group between 7 and 8. All right, so The synthesis when we're doing them is we have an acetylene, and we can only add 2 carbons at a time. So we would add NaNH2, and then the best way is to add this ethyl bromine, bromoethane, to add those 2 carbons. So that's my first thing. But the problem with this, not a problem necessarily, but we have to use acetylene as our source of carbon atoms, which means that I need to make that bromoethane. So I'll just do that over here. So we have bromoethane from this. This is our target molecule. So to make that, I need to reduce this to the alkene. And then I can just add HBr. So we'll call that A, and I've already made that. So in this particular synthesis here, we've already added our, if you want to think about this, carbon 7, 8, 9, and 10. So we just need to add 1 through 6. And so you can just do the same thing repeatedly. So I have that. I'm going to add to the other side. Actually, how many? I need to add 6 carbons. What I could do instead here actually is to reduce this to the double bond. So that's 4, and then I can do HBr ROOR. And then take, this is B, acetylene, a different acetylene now. And add the bromobutane. And that will give me my 6 carbons. Okay, and then I can turn this into the Br. So H2 Lindlar. And then HBr ROOR. And then I can add that to the original one that I made there. This one.
I like the color. It's like golden.
To get to the target molecule. So you could add the 2 carbons at a time, and where I paused here with this step, we'll call that number 1. Instead of adding extra carbons on the other side, if I did that, I would have the functional group in the middle of the compound, which would make it add more steps. So the smarter thing to do is to add this whole 1 through 6 carbon in one chain instead. All right, any questions there? Okay, so this was probably a lot. You can take some time to process it. I'll post that video with the extra problems this evening so that you have access to that. if you want to look at extra problems, or at least me walking you through those extra problems. If you have questions, you want to stick around after class, you are free to do so. Otherwise, I will see you guys tomorrow.